Okay, see, we will continue our discussion on the turning maneuver. I will bring back the last slide of my last lecture. What I was trying to mention, that you see in the last class we found out that in a turning maneuver, my R by L, when R is the steady turning radius, L is of course ship length, is given by this expression, and the drift angle minus beta given by this expression. See, what therefore we are trying to tell is that if I look at this first expression, you will find out that from expression this top part is actually the C, this C, that is the stability index. Now, for a stable ship, this C is supposed to be positive. Okay. If you take this into account, you will find out that R is inversely proportional to delta, and also if I take the proper signs, you will find out that it will always turn. If I were to give a negative ship, will always turn this side. Okay. So, this too will find out, that is the direction of turn, etc., because we can put this proper sign. I will leave that, as I said to you, for exercise from the signs, from the signs of various terms, etc. The other thing you find out is that R by L is independent of speed. This is something that people never realizes, at least within this linear theory. Why? Because there is no scope of V coming, that the speed coming. You see, these terms are all independent of speed, ship speed. If I were to make dimensional also, then it will be all half rho L V square, etc. all will get, you can check yourself, will all get cancelled from both sides. So, interestingly, therefore, the ship going at 10 knots or 20 knots or 30 knots, if you give 30-degree rudder, it is going to have a same turning radius. What differs? You know what differs? Basically, the time taken is different. The time that it takes to execute becomes much faster, because it is going at a much faster speed. But the circle will remain same. That means, if I were to do a simulation, I will find that this will remain like that only. It's just that it will become faster. That is point 1. Point 2 is also with respect to the drift angle. You see, the drift angle also, I will leave it to you. You will find that the drift angle is in direct proportional to delta, which means that if I give larger rudder, okay, I have larger drift. That makes it very interesting point. That means, if I give larger rudder, then what happens? The ship turns at a quicker turn with a larger drift angle. And if it is a smaller rudder, and drift angle is smaller. Okay. So, this is also very interesting, because if I want a larger turn, then it turns out that I have a larger drift angle. In fact, this drift, now you will find out interestingly that this drift angle delta beta, if radius is made infinity, then beta becomes 0, which basically means beta can only become 0 when it goes on a straight line, because R infinity is a straight line. But if you were to turn, you have to have a beta. That the point is very taken. You cannot have a ship turning exactly like this. You just cannot have. Beta is a necessary condition, the existence of beta, for a ship to have turn. You can see it from there. That is, these are all interesting consequences of that. What happens when the C is negative? In fact, if C is negative, this part becomes negative. So, you have no definition, because when C is negative, you will find out these solutions do not hold good. And in fact, if you see R by L part, you will find that it will become opposite within a limit. Of course, it is not very true, but if this is negative, exactly opposite side, it is going to be basically ship will turn. Okay. So, of course, that is not cannot be stretched much, because this part becomes denominator here becomes 0 and it becomes infinity. But these observations are very interesting. Now, we will look into this behavior part of why initially the ship has turned on this side and what are the hill along with that. Let us look at that. But see, initially I mentioned that as the ship goes, it basically goes this way. In the first phase, approach phase, it has actually gone to this side, even though I have given rudder here. Okay. Why? Let us look at these pictures of the hull. This center of gravity here, this bottom line. Let us say rudder will be somewhere here. Typically rudders are here, no? Okay. So, you end up getting a force here, that is m v dot plus m x g r dot. In fact, this will come out from this equation of motion, you will find out. M v dot and m x g r dot. This two actually comes out, these two equations. No, not on, let me put it on this one, or let me see this from this the old equation one. I just want to show you why this, or rather on just give me a second, I will locate this and see here. This is my old equation that I had in last lecture. Now, if you find this inertia forces, you have got m v dot and m x g r dot and m u r, etc. These are the terms that are coming. For acceleration, this is m v dot and m x g r dot. This is actually the centripetal acceleration force, basically. That's what is happening. So, this is there. But that one. Now, the thing is that why I am writing this is because this when you are actually accelerating, and of course, you actually also have here this side, that m into u r. This is the other term, that is this. If you look at that, you will find out depending on the sign and all that. I will just leave it. And here the hull forces come, okay, y v dot plus y r dot plus y v plus y r r. And this side comes the y delta. Basically, these are the forces, balancing of the forces. Now, there is a what you call m v square by r force that will come. That is this one, m v square by r, etc. As it is turning here on the right hand side. So, there is a force coming on the outside. Remember, this is turning on inward. This vessel here is turning this way. We are looking at the cross section point view. Now, what happens in initial phases, what is happening is that I gave a large y delta, okay, initially, because I just applied the rudder. My v dot and r dot are small values, and actually y v dot y r dot is typically smaller than this, and this force represented smaller than this normally. So, what happened, although I gave that, first I gave a push on this side. Before the hull could react, the hull has got shifted this side. See, before, this is the thing, I give a push this side. As I give a push this side, before it could turn, it actually got pushed this side. And then, of course, the heading will turn. So, this is why at the initial stages, because of this y delta, the ship moves this side. Okay. Not only that, if I were to take moment about this point, this forces are very small. Which side the heeling moment will come? It will actually turn out to be this way. The heeling moment will turn out in this case, in the first phase, to be something like this way. Ship is turning that side. So, what will happen? It is going to turn inwards to the circle, So, this is gone. Now, we will look at the third phase. In the well, let me look at third and then come back to second. In the third phase, what happens? This has now fully established, this term. Remember, this is not there, but this is there. Now, this hull force, this part is actually much larger than this, typically, these hull forces. As a result, my force is more net force. I'll establish this relation, and we will even do a problem. This part of the force in the third phase is larger than this part, which means there is a net force on this side. Then what happened? The net moment is on the other side. So, the ship turns on the other side. But before that, that means, let me put it this way, initially if I see with time, initially my heel, so let me call inward is plus. So, I have actually slightly plus, but then finally I have got steady minus, because this force has become more. But in between that, when both of them are there, this part has been larger, because when this also is present with respect to this, then my this side moment is even larger than having only this part. That means this is actually larger. So, what would happen? It basically would have shot it here and then come down to like that. This is how it will look like, the heeling. That is phase 2. I would have actually overshot the heel and then ultimately gone like that. So, this is how the heel will look like. Okay. So, this is very and you will find a picture always that the ship is, there is a classical picture of aircraft carrier, I have on my table, you will see as the turning is outward. That means if you fall from the deck, or if a aircraft fall, it will be outside the loop. See, if you are turning here, the slope is this way, so you will fall outside for a ship, not inside. When you are turning, you will find you are turning, as I told you, with like this way orientation you are turning. Okay. The interesting point here is that, see, this I will also explain, but from physical you can understand. Now, suppose you are turning, you are here, you are turning, we are outward. Now, suddenly the captain decides that I am going to stop the rudder, bring the rudder to 0 quickly. What would happen? Remember, the net force acting here is this minus that, which gives me the moment. See, once again, this minus this gives me the moment, which gives me heeling. Now, suddenly I make this as 0. What would happen? This is actually become suddenly more. So, it is basically going to have a snap roll outside. It is going to actually certainly go further rolling instantly, and therefore, it may capsize. See, you can, I will show this now with respect to a kind of equation form, but just I want you to see the physics of it. Basically, what I am saying is that, see, or rather let me show it in another diagram with respect to this way, just that part of the force. Never mind the G force, because we are taking moment about the G line always. See, here I am just looking this force is at, see, there I have a force here this side, and I have more or less a force here this side. This is rudder force, this is rudder, this is hull. So, this net force give me, obviously, approximately I will work this out, something like this, that is a net force. This about this gives a moment, agreed. Now, what happened? Suddenly you bring this to 0, suddenly, not slowly, we are talking of this time element. Then suddenly this much of force will act, that means the moment acting here to turn is suddenly increased. So, therefore, the ship is going to have a snap roll, and eventually it may this thing, but this may snap, this what is called snap roll, it might be more than the the stability angle. So, it might actually capsize. So, this is always a bit dangerous, this part is always a bit dangerous. That is why when you are kind of turning steadily, you should not bring the rudder to 0 on very quickly, you must bring it very slowly. And I tell you, many small boats that capsizes, it is not only the static stability loss, it is also because during turn there is a heel and dynamic effects, rudder forces come in play. Many capsize actually occurs, small boats actually during turn, because during turn there is a tendency, just imagine that also, that if you are turning and you are going heeling outward, and then everybody also moves outward, then there is a further shift of weight outward, then there is a free surface effect, water moving to this side. So that causes further augmentation of the problem when you are turning, because you are moving outward. Okay, so this is an important point, that when we talk of safety during turn, the heel becomes very important. But we will find out that for large ships the heels are very small angles. Let us now work out how do we calculate heel angle during steady roll. Let's go it this way. No, steady turn, sorry. Let's look at this. I will do it in a simple way, and then we also do a problem too. This is rudder. mv square. This is a centrifugal force. That is basically MUR. If you look at that, it will become like that. MU square by R, V square by R, whatever. Let's call this to be the hull force, FH. Oh, sorry. Acting at the point E. Let's call this F rudder, acting at the point H, and this is a point keel. See, what we are drawing here is something like this. Maybe I should have explained there. This is my center of gravity. We will of course take the moment about that, so we don't really so much care, but we will have to have this is all during steady turn. Remember that dot part which I dot earlier is not there. Remember these forces are not there. This is not there, this is not there, because we are on a steady turn. There is no V dot nor R dot. All that we have got is this one, which is nothing but this one. Basically this part MUR is nothing but this mv square by R, capital R, with a U will come within the R, this capital R. This mv square by R, everybody knows that. Essentially that is m into U into small r, which is the same thing. You can check that. Now what we are saying, that typically rudder is somewhere here below that. For typical ship we are talking, center of gravity is normally slightly above that. If you call this to be, say, draft here, rudder is somewhere approximately around the draft. Middle of that rudder, let me call this that H is the point we are saying where the rudder force acts, resultant rudder force approximately, and if FH is acting, let us say at a point E, and this is my point keel here. So what do we have here is simply something like that, FH minus FR equal to mv square by R. That from net force has to balance. Total F means total Y force here essentially 0. That it comes from the equation also, if you look at that, because after all FR will be Y delta delta, FH is going to be YVV plus YRR. Essentially if you look at that, it becomes that, but I am just looking at that way. The moment causing heel, this is going to be FH minus, I will just follow this here, into kg is straightforward. We have done, that net force this side into K2G. If you work it out, it's very simple. Basically, I mean, I don't even have to explain that. It is absolutely straightforward to just take moment about these distances, etc. So ultimately, what I want to say is something like that. It will become See here, actually if you look at that, it becomes very simple. Fr minus Fh, Fh minus Fr is this side force into Ge, G to E distance, minus Fr into Eh, Fr into E to H is this distance. I mean, it is a very simple thing. What the point of saying of all this is that is very simple. For most ships, you would expect E and H to be very much close by. Why? Because you remember that Fh is expected to be acting approximately halfway through the draft, right? An approximate value we are talking. If you don't want approximation, you can always do the exact one. Radar by choice, you normally have again almost like the draft. In fact, if you think, you will find the radar area is slightly tapered upwards, so that center of gravity is slightly above the midway, and so will be the pressure, because more fuller form on the top. So essentially EH can be approximately this, maybe it is close to 0, so that my heeling moment turns out to be essentially this, where GE is, you can say GE is G to E, and E can be taken as middle of the draft. The E can be taken, this can be taken as T by 2 if T is the draft. Okay. So what is happening is very simple. You as if you look at other way around, as if the same point both the force acting. So my net force this side becomes obviously, or this side becomes Fr minus Fh, or this side becomes Fh minus Fr, and you take the moment. Actually, I told you Fh is more than Fr, so it better to take Fh minus Fr. Fh is basically YVV plus YRR. Typically that is much more. So it is, and of course it has to be, because remember again this also is obvious, because Fh minus Fr is this. So obviously Fh minus Fr has to be more, because it is turning this side, there is a lateral force, so the force has to be coming inward. So then what we end up getting is absolutely straightforward. Of course, we end up getting the fact that my heeling moment, let me write it in the next slide. But you see Fh minus Fr was mv square by r, Fh minus Fr was mv square by r. So if I put that, this will become what is the heeling moment? If suppose the ship is heeling phi, this heeling moment is what? M into G, that is weight, into Zz. Zz is what? Gm into phi. So we have got, so from there what do I get? M gets cancelled out, okay. Very simple. This is only approximate. But anyhow, what do you find again? See, we are only going to look at this part. In this, of course, you will find a relation with V. V is a here remember V is a forward speed. That's what mv square by r, when you do V is a forward speed, your force depends on forward speed. So you see, now you see here phi is in proportion to V square. Means if you go at higher speed, yes, you may have a stem radius, but you are going to heel more. Phi is inversely proportional to 1 by r. You have a tighter turn, you heel more, right. So if you get large, now you have a larger rudder, obviously if you get larger rudder angle, I mean larger rudder means tighter r, means r is proportional to delta, isn't it? or yeah, no, so inverse proportional to delta, right, proportional to delta. So you understand that if I give larger rudder angle, I have a tighter turn, I have a larger heel angle outward. If I go faster, my radius of turn is same, but my heel angle is larger. And so if I am going at it very fast with a large heel angle and suddenly bring back my rudder to 0, I actually am looking at a dangerous situation. Okay. So let us, for example, this is straight formula. You can use sine, these are approximate. I presume here sine phi as phi because phi is small. If you don't like, you can put sine phi. Let's have a, for example, a small problem that it is here. Let me just work this out. See, it says for heel during turn that the vessel turns draft is that's what it says. See here, this ship is here. Draft is given as 5. This is my kill point K. K to G is 6 meter. Okay. Metacentric height, of course, metacentric height is 2. My rudder force Y R is given 1.5 mega Newton, but this doesn't become actually important here. Now you see my formula, if I go back, I have phi is V square RG into GE, right? Let me put it down. Now GE, this is my E. What is E? E is my point of action. What do I take GE? I will take this to be 2.5 meter approximately after all I am doing. See, this is 5 meter. So exactly, so this is 2.5 at 2.5. So GE become approximately 3.5 meter. Okay. So my formula for GMT of course is given 2. So phi becomes V square by RG into GE V here is 20 knots. So it is 20 into point. Okay. V is 0.5144 by R is 300 meter, G is 9.8 say, into GE becomes 3.5 meter, right? So if you work it out, this will turn out to approximately, I am not doing the full bar, but if you work it out, what this interesting points you will see, that mass is not coming in picture also in this equation. Rudder force is not coming in picture, although I have given rudder force here. The reason is because rudder force and hull force, this difference comes in picture, which is given by this because of the balance. No, mv square by r, and the m of course gets deducted for the roll part. Okay. So this is the interesting point that you will find out here. Okay. So here, although I gave 1.5 meganewton rudder force, not necessary. Now tell me one thing. So like that we can work it out approximately. It is not much, 3.5 degree. Normally, the hill during turn can be about 5 degrees, 6 degrees. It can even maybe 7, 8 degree or so. You can see some nice pictures. As I said, there is a very nice picture of this aircraft carrier, US, the turning, and you can see it's on turning on the outside. And turning outside is always more dangerous after all, because things will fall outward. You know, if you fall overboard, you'll be falling outside the loop, not inside the loop. Now tell me, what would be the hill for a submarine? Typically, for a submerged body, typically, I am not saying it's fixed. You see here, what would happen? Normally, you see here, center of buoyancy will be here. Center of gravity is going to be below the center of buoyancy for stability purpose. Okay. Now, your rudder are normally central, whichever. So, it is somewhere here, and rudder force is going to be more or less, and hull forces going to be somewhere here and here, whereas mv square by is going to be at bottom location. Compare that to this. Compare that to this, or what we have done in this other, this one. Compare that. See here, my G point was above the point of action of the hull forces, but for a submarine, typically, because of my stability, my center of buoyancy has to be above center of gravity. You agree with that, because center of buoyancy is meta center for submerged body. So, center of gravity has to be below that. So, G typically is below point B, and B is of course the point more or less where the hull and rudder acts. That means, B is equal to my E point, G is equal to the G point, but here it is opposite, G is below. So, which side it is supposed to hill? It will obviously hill inwards, right, because it will hill inwards now, because the direction has changed now. You know that this thing, about that if you take this thing, this moment is going to be like that, while inward turn. More or less, you cannot say for guaranteed, but more or less for a submerged body, usually the hill will be inwards, although it is very approximate, because to find out hill you have to find out all kind of interplay of the hull forces, which is not small. Number of hull forces will be coming. Here of course, we just made an approximation. In fact, in submarine and all, things are much more complicated, because as it turns, you know, if you make it turn, it also goes down or goes up, it does not stay in the same plane, because as it turns, I mean, I just on the side want to tell you how the hull forces come. As it turns in horizontal plane, it necessarily produces an upward or downward vertical force, pitch and all. So, therefore, what would happen? If it is upward force, it will pitch up, and so it will spiral up, or it will spiral down. Mostly by design, you design it such that it spirals up. Mostly, in fact, submerged body things are much more complicated. Even if you want to go on a straight line, it will actually surface, because the top and bottom are not symmetric. Typically, you know, like I just on the digressing little bit, but if you see that the top part of the flow, the bottom part is not same. So, as you go this side, there is a net force and net moment coming, and it tries to go up. So, therefore, why this is important? Therefore, you cannot study the horizontal turning or vertical without the coupling for submerged bodies. You cannot say in isolation I will make it turn, because it turns, it spirals down, because horizontal motion necessarily produces vertical force. Vertical may not produce horizontal because of port starboard symmetry, but horizontal does produce always vertical. But what I am saying, in a straight line motion also, unlike in a ship, because there is no buoyancy equal to weight, hydrodynamic force becomes much more critical, because you know in a ship, in this plane, you push it down, buoyancy will push it up. Buoyancy force is so large, right? Push it down, you push it up, get pushed up. But in a submarine, you push it down, come down. So, what will actually cause it to go up? Only hydrodynamic force. So, hydrodynamic role of hydrodynamics becomes even more critical, vertical plane, for submerged bodies. You know, slight forces can cause it drift. I mean, you can see that. And I was remembering your this thing, that slight forces, there is no propeller, but body keeps drifting. Okay. So, we have said this. Now, I am just going to spend some little time on trying to tell about some of this, what I should say, IMO requirements on this stability issues. Before, if you have time, we can go to some vertical plane motion. See, we have just more or less understood turning behavior, hill during turn, etc., etc. We now know why we should not suddenly stop the rudder while turning. We also know the radius of turn really don't depend on speed as much, but the heel angle depends, forces depend. Radius of turn doesn't depend because it's an interplay of force by force, so it becomes neutralized, the additional force, etc., etc. Having said all that, you know that regulatory bodies, all regulatory bodies they have to stipulate some requirement of what do you call a good maneuvering or acceptable maneuvering criteria. Like your stability, we have got IMO requirements, stability criteria. So there are similarly criteria which is, I can tell you, IMO 1993. I want to just mention the resolution A75. Oh, sorry. On what is called interim standards for ship maneuverability. Some of the points, salient points I want to tell, some of, not all, because then you understand that you have designed a ship. So you understand what characteristic or what like properties as far as maneuvering is concerned the ship must satisfy. Nobody actually stipulates usually that you have to achieve that, but there is an upper bound like stability, and most of these rules are connected to safety. Whether you are able to turn or you are not able to turn, the rules don't say, but you should have safe maneuvering characteristics. So I want to just mention a few of them, okay, this application of these rules. Only a few points. So there are some rules given. It applies essentially to zigzag maneuver and turning maneuver and also stopping trial, but I will not tell. In other words, basically you have to make sure that your ship is within those limits. Why I am saying? Because you will find out that the limit in zigzag especially, it is not that you have a very highly maneuverable ship. Basically there are limits on both sides. So here some of this thing is like this. The test speeds, the important one only I am writing. Corresponding to I thought this is an important point, one point. See, this standard will be applied at a speed which will be minimum 90% at minimum corresponding to 80% of the engine power, which means you stipulate a speed, you have to do the test at that speed, not at a very low speed or high speed or something like that. Okay, then they apply for this thing will apply for although it is says this is the rules have been made for more than 100-meter long ships, nowadays many people are applying them in for smaller vessels also, just because otherwise there is no criteria really. And there are many other things deep under. I just want to tell you about the actual criteria with respect to the maneuvering, rather than many. See, any rules will have many stipulations. For example, it will say the standard of maneuver should be performed without use of maneuvering aid. Condition of standard apply in deep unrestricted water, calm environment, full load, even keel, like that. So many are there. But let me just look at this criteria. The criteria are. This is the most important one. Now turning. See, turning ability. Now you will see what. When you are doing a design, this becomes important. You have to make sure that your design conforms to these standards. See here, the advance. The here advance means the distance it moves forward when it has changed 90-degree heading, which is also like specified earlier. The advance, the word advance in the rule they also said what is advance, etc. Advance. See, this is one. Should not exceed 5L. See here, I want to tell you this. If you look back in my very one of this earlier this diagram of advance and transfer, I'll just bring back this. I just take the advantage of. You see here, transfer is this, or tactical diameter is this. Okay, advance is this. Turning circle is this. Now turning circle is not entering in picture here, which is what I have given in another diagram. That okay, here also. So this rule applies only to. I am just drawing an exaggerated diagram. It is applying only to advance and transfer. It is not applied to R. Obviously, then moment that is so, these rules are basically safety rules, because it wants to make sure it doesn't go beyond some length in the x direction, beyond some width in the y direction, whatever the turning is. Okay. So these are basically safety rules. You can easily see that from this stipulation here. And when you so therefore really the rule doesn't bother whether you are able to turn or not. It simply says if you want to turn, make sure you don't hit the other side. It's so much of waterfront in front, and make sure you don't hit the right hand side. That's what it says. Then this is one rule. Then there is another one called initial turning ability. The next one. Let me write it here only. By the way, okay, I mentioned that a little later. Here, okay, this also, this turning ability I should have mentioned also here, that this turning ability has to be done at 35 degree of rudder, or at the maximum rudder for which the ship is designed. Okay, this also is specified there, the standard. Yeah, I didn't mention that. This is very important. At this here, turning circle is to be maneuvered with 35 degree of rudder or maximum rudder angle permissible at test speed, following a steady approach with 0 yaw rate. So this is to be at a 35 degree of rudder. Let me also tell you delta. This test also has to be done port and starboard. Now I will also tell you this. Tell me, for a typical ship, do you really expect the port turn and starboard turn exactly symmetric? Why not? If it is not symmetric, why not? Before I write that, let me continue on that. Why is it that port side turn and starboard side turn? The test says, why I am saying this, the test says, I did not specify, this is only telling only one criteria, but this test has to be done at 35-degree rudder or at the maximum rudder permissible as you design. Most ships are designed 35-degree rudder, but for both port and starboard sides. My question is, why both port and starboard sides then? Give me a reason why. What could be a possible cause why port turn and starboard turn may be asymmetric? Slightly, even if slightly. No. See, remember that the forces depend on the hull shape. Hull shape is symmetric purely. See, the answer is in propeller. Mostly, remember, the rudder is behind a propeller. Okay, and the propeller is a single screw propeller. Propeller has asymmetry. It is moving in one direction. So the flow has slight asymmetry in one side. Remember that the propeller moves in one side if it is single propeller. If it is a twin propeller, it will be much less, theoretically not, will be 0. But single propeller, you will obviously, if the propeller is this side, there is a bias for the flow on one side. So the rudder in this side and rudder in that side will not perform in the same way. That is why they say that you must do the test on both sides. Okay, that we did not do this kind of modeling, and this kind of modeling will come in when we discuss later on full nonlinear simulation with all kind of hydrodynamic forces. Now let me write the other two quickly. This criteria, it says the with application of see, read this. Initial turning ability. With application of 10-degree rudder, the ship should not have travelled more than 2.5 ship length. Means with you have given a rudder somewhere here. It should 10-degree rudder only. It should not have gone beyond this length 2.5. By the time its heading has changed to 10-degree. What it means? Supposing it has gone beyond, what it means, it basically means that it is responding very slowly to rudder. See, after all, supposing, what does again say? It stipulates a condition on how fast it will respond to rudder. Because imagine, it is going at a full speed, you give a rudder, it is responding so slowly that it has actually gone much farther by the time the heading has changed 10-degree. Not accepted. It says you must have the heading change 10-degree before you have reached 2.5 L along the x direction. See, the ship should not have travelled more than 2.5 length by the time the heading changed to 10-degree. So it basically tells initial responsiveness of the hull to the rudder. Initially, the hull must respond, because otherwise it shows it is very sluggish. It is responding much late. Maybe it will achieve a turn, but that would imply actually something like this. See, this is actually the picture. I'll show you. The difference is that one ship will be turning like that, another ship may be going. This is not accepted, because this one means you are actually coming much higher, but yet you don't have actually the turning rate. So that is this condition stipulates this basically. That means it puts a boundary on how initially it will respond. Let me quickly go to this the zigzag maneuver. The zigzag maneuver or yaw check or course keeping, it says. See the should not exceed see here I this is again interesting. I'll just let me draw this diagram. This see this overshoots here. Huh? Say this is like that. So this is my first overshoot. Okay, this. What it says, you know, why I am telling in a 10-10 maneuver, 10 degree zigzag, it says it puts a limit based on, of course, L by V. That means there is a dependence on length and speed, by which it says that I must have a limitation of my first overshoot. It cannot be more than some value. See. And the second also there is a limitation, that is this plus 15. That means the rule has put a limitation on the overshoot angle. It cannot exceed the overshoot angle more. Again, for safety, that you have to make sure that your ship. Now you see why I am saying this. I told yesterday's class that if suppose a ship is highly maneuverable, then it normally reaches faster but overshoots much more, not accepted. So you cannot have a ship which actually goes overshooting like that. No. See, a ship which is highly maneuverable will try to do that very quickly turn, but no, you cannot have that beyond certain limit. That is what is stipulation. Exactly the same stipulation I will just have to write very quickly. 20-20 maneuver in for 20, because we are 20 zigzag. It says the first overshoot should be less than 25 degree. It says that in 20-20 maneuver, first overshoot will be less than 25 degree. That is the other criteria. Then there is the final one. I will just end up stopping criteria. It says, which we have not talked. The length of stoppage should be less than 15 ship length. Track. See, suppose you are stopping the engine, then it will basically go like that and ultimately stop here, because it will never be straight line, because you put a radar and all. So this distance less than 15 L, it says. So what I am saying, that this is the never mind the stopping criteria, but zigzag maneuver you have seen that basically it is stipulating a limit on the top. Okay. So I will end it at this point, but I want to just mention saying, therefore what happens for ship these trials is that you conduct the trials, you know the assessment, but from rule point of view you have to make sure that you are satisfying this criteria. If you don't satisfy the criteria, they will not approve it. Okay. So and you can see the criteria are all both ways. You cannot really have too maneuverable a ship, because then this criteria may be exceeding, etc., etc. So with that I am ending here. We will see what we do next class. Thank you.